Okay, let's go. Number 1. The Dark Flow. You are Alexander Kashlinsky, a senior astrophysicist at NASA's Goddard Space Flight Center. The year is 2008. You've spent 4 years analyzing the motion of galaxy clusters, enormous gravitational structures, each containing hundreds of individual galaxies, using temperature data from the Wilkinson Microwave Anisotropy Probe. The work is painstaking, the data set enormous, and what you've found doesn't have an explanation. Hundreds of galaxy clusters, scattered across billions of light-years of space, are moving, not randomly, not outward in all directions the way the expanding universe predicts. They're moving together, in the same direction, at the same speed, toward a single point, a point that lies beyond the edge of what we can observe. There is nothing there because there is outside the observable universe. It's a region of space we can never reach, not with any telescope ever built, not in principle, not ever. You publish the finding. You call it the dark flow. Here's what makes this impossible. The universe, according to standard cosmology, expands uniformly, on the largest scales. No direction should be preferred over any other. Space pulls galaxies away from each other equally in all directions. The dark flow violates this at a fundamental level. Kashlinsky's team surveyed more than 800 galaxy clusters, spanning distances from 300 million to 3 billion light-years, and found them all streaming at 600 to 1,000 kilometers per second, toward a patch of sky in the direction of the Centaurus Hydravella region. Not a single cluster moved against the flow. When Kashlinsky published a follow-up study in 2010 using 1,400 clusters, the result held. The flow wasn't an artifact of their sample size. It was real, it was large, and it was consistent across every data cut they tried. The source of the gravitational pull has to be beyond the cosmic horizon, the boundary past which light has not had time to reach us since the Big Bang. Anything beyond that boundary is permanently invisible. We cannot observe it with any wavelength. We cannot send a probe there. We can calculate its approximate direction in the sky, but we will never know its nature, its distance, or its composition. Something massive enough to drag hundreds of galaxy clusters across billions of light-years has been pulling for more than 13 billion years, operating since before most of the universe's stars had formed. It exists beyond a horizon we can never cross. Think about what that means. Something outside the observable universe, something we are physically prohibited from ever seeing, has been announcing its presence through gravitational influence since before stars existed. The announcement has been running continuously for 13 billion years. We noticed it in 2008. The mainstream explanation treats this as a measurement artifact. Competing analyses using the Planck satellite failed to detect the same signal at high confidence, and some researchers argue that Kashlinsky's method for isolating cluster motion from background noise introduced systematic bias. In this view, the dark flow is an apparent alignment that dissolves under improved methodology. But Kashlinsky's results survived multiple rounds of scrutiny and were reproduced with progressively larger samples. His team published detailed responses to the specific criticisms raised by the Planck analysis. The debate in the scientific literature is ongoing. No one has produced a definitive refutation, only competing analyses with different assumptions. The dark flow remains in the published record, unresolved, 16 years after it first appeared. What lies beyond the cosmic horizon, pulling everything in one direction for longer than our sun has existed? Is this a density fluctuation left by inflation before the Big Bang, or something that exceeds what our cosmology has room for? And if something beyond the edge of existence is producing a gravitational effect we can measure, what else is it producing that we haven't found yet? Number 2. The 234-star laser signal. You are Ermanno Borra, an astrophysicist at Laval University in Quebec. It's 2016. You've been working through spectral data from the Sloan Digital Sky Survey, one of the largest astronomical datasets ever assembled, containing the measured light signatures of more than 2.5 million stars. You're looking for something specific, unusual periodic modulations in the spectra, rapid intensity variations that don't fit stellar physics. Most of the 2.5 million entries are clean. Then you find 234 that are not. All 234 have the same anomaly. The same rapid periodic modulation, pulsing at the same interval. In 234 completely different, completely unrelated stars, separated by vast distances across the galaxy, you are seeing the same signal. The paper Borra published with his collaborator Eric Trottier appeared in the Publications of the Astronomical Society of the Pacific in October 2016. The anomaly was a periodic spectral modulation, repeating every 1.65 picoseconds, a trillionth of a second, appearing identically across all 234 stars. Natural stellar physics does not produce periodic spectral modulations at that interval. Stellar spectra encode information about temperature, composition, magnetic activity, and rotation, none of which generate rapid optical oscillations at this frequency. When Borra and Trottier worked through the standard list of known instrumental effects that could create false periodicity in the dataset, they couldn't account for the signal. Here's where it gets strange. All 234 stars fall within a specific spectral class, F2 Tacone. That classification corresponds to stars roughly similar in size and temperature to our own Sun, the stars considered most likely to host planets in habitable zones. Out of 2.5 million stellar spectra, the anomaly appeared in exactly 234, and those 234 are disproportionately solar type. If this were a random instrumental artifact in the data pipeline, it should appear across all spectral types in proportion to how many of each type exist in the catalog, or it should contaminate far larger numbers across the board. The selectivity is the problem the instrumental explanation has never cleanly answered. The SETI Institute reviewed the paper. They noted that the described modulation pattern is theoretically consistent with what an extraterrestrial civilization might produce if broadcasting laser-based optical signals toward a large number of stellar targets. Simultaneously, they did not dismiss the paper. They recommended further observation with independent instrumentation. The mainstream explanation holds that the most likely source is a systematic artifact in the SDSS spectrograph or its data reduction pipeline, some instrumental effect that introduces false periodicity at specific frequencies, appearing in a subset of the processed data. Instrumental artifacts are real. They affect large spectroscopic surveys, and they can mimic astrophysical signals. This is a legitimate concern, but if an artifact creates a false signal in the pipeline, it should contaminate spectra of all stellar types in proportion to their representation in the catalog. The catalog contains far more K-type and M-type stars than F-type. The 234 stars with the anomaly should be distributed accordingly. They are not. They cluster in the solar type range. No follow-up paper has produced a specific, documented instrumental mechanism that explains both the modulation and the spectral type clustering simultaneously. No independent large-scale survey has yet been conducted with a different spectrograph to either confirm or definitively rule out the finding. The original data is real. The signal in those 234 spectra is real. What produced it is unanswered. Why do 234 Sun-like stars share an identical spectral modulation that no known stellar process produces? If this is an instrumental artifact, why does it preferentially appear in solar-type stars? Why does the modulation interval match theoretical predictions for what optical transmission signals from another civilization would look like? And nobody has explained the selectivity. In 2017, something crossed into our solar system from outside, not a signal, but a physical object, and it didn't behave like anything in the catalog either. Number 3. Oumuamua. You are Robert Warwick, an astronomer working with the Pan-STARRS telescope on the summit of Haleakala in Hawaii. It's October 19th, 2017. You're reviewing data from the previous night's sky survey when you find a point of light moving in a way that immediately flags as wrong. The trajectory isn't the arc of an asteroid. It isn't the elliptical path of a comet bound to our sun. It's hyperbolic. The object came from outside our solar system, and it's leaving on the same kind of trajectory, faster than the sun's gravity can hold. In 40 years of systematic sky surveys, no one has ever confirmed a visitor from interstellar space. This is the first one. You name it Oumuamua Hawaiian for a messenger from afar arriving first. The object was already past its closest approach to the sun when Warwick found it. Astronomers scrambled every available telescope to gather data before it left the inner solar system entirely. What the data showed broke the catalog. Oumuamua's rotation tumbling end over end every 7.34 hours, with extreme brightness variation, suggested an aspect ratio of roughly 10 to 1, far more elongated than any known asteroid or comet. Its surface was reddish, consistent with long exposure to cosmic ray bombardment during an interstellar crossing. And it showed no coma, no tail, no spectral signature of outgassing. Whatever it was made of, it was not shedding material in the sunlight the way every known comet does when heated by a star. Here's what makes it impossible. As Oumuamua moved away from the sun, it accelerated, not by the amount solar gravity predicts. More than that, it was being pushed beyond what gravity alone could explain. Astronomers ran through every candidate source of that extra push. The only one that fit the data was radiation pressure, the gentle force of sunlight against a surface. But for radiation pressure to produce that much thrust from a body this size, the object would have to be extraordinarily thin. Estimates placed it at roughly a millimeter in thickness across a surface hundreds of yards wide. That is the geometry of a solar sail. Harvard astrophysicist Avi Loeb and his colleague Shmuel Bialy published a paper in the Astrophysical Journal Letters in 2018 proposing exactly that. Oumuamua's acceleration profile was consistent with a thin, flat artificial structure being propelled by stellar radiation pressure. Loeb was not a fringe voice. He was the chair of Harvard's astronomy department. He wasn't claiming certainty, he was documenting that the data fit the solar sail hypothesis and that the natural alternatives each had serious specific problems. The mainstream explanation cycles through several candidates. A hydrogen iceberg could sublimate without visible outgassing, providing thrust. A fragment of nitrogen ice from a Pluto-like body could behave similarly. Both are real physical possibilities. But hydrogen ice is cosmically fragile and would have evaporated during millions of years of interstellar travel. Nitrogen ice requires the disruption of a planet-sized body in a specific and rare process. More specifically, no single natural model explains all the anomalies simultaneously. The extreme elongation, the absence of any outgassing, the non-gravitational acceleration precisely directed radially from the Sun, and the galactic rest velocity near zero. That last detail is the one that stays with you. When we found Oumuamua, it was moving at nearly zero velocity relative to the galaxy's center of mass, as if it had been placed there, stationary, and then swept up as the Sun passed through. As if it was waiting. Why did Oumuamua have near-zero galactic rest velocity, placing it almost precisely in our solar system's path? What produced the excess acceleration with no detectable propulsion mechanism? Why does its thrust profile match solar sail physics so precisely, while no other natural explanation fits all the data simultaneously? Oumuamua left the solar system in 2018. The questions did not leave with it. Number 4. The 16.35-day clock. You are a radio astronomer, working with the CHIME telescope, the Canadian Hydrogen Intensity Mapping Experiment, a massive array of radio receivers spread across a field in British Columbia. It's early 2020. You've been analyzing months of data from a repeating fast radio burst source, one of the few known to fire more than once. Fast radio bursts are millisecond-long blasts of radio energy so intense that a single burst can release as much energy as the Sun produces across 3 days. Most fire once and never repeat. This one keeps firing. And when you map its timing across the full dataset, you find a pattern that should not exist. The source fires for approximately 4 days. Then it goes silent for 12 days. Then it fires again for 4 days. Then 12 days of silence. Every time. Precisely. Like a clock. The source is designated FRB 20180916B. The CHIME team published their analysis in Nature in February 2020. The repeating cycle runs 16.35 days with an uncertainty of only 0.15 days. Precision confirmed across multiple observation windows spanning more than a year of accumulated data. The source is located approximately 500 million light-years from Earth in a spiral galaxy. The period doesn't drift. It doesn't smear. It repeats at the same interval each time, regardless of which observation window you use to measure it. Here's where it gets strange. Fast radio bursts are produced by some of the most violent processes in the universe, almost certainly involving magnetars, the ultramagnetic remnants of massive stars, or other compact stellar remnants, operating at extreme physical limits. These are not scheduled phenomena. Known pulsars, the most regular natural clocks in the universe, pulse on timescales of milliseconds to seconds. Some binary systems modulate radio emission over days or weeks, where a companion star's wind or orbital geometry periodically blocks or modulates the burst source. The period in those cases is set by orbital mechanics, and it shifts gradually as the system evolves. The mainstream explanation proposes exactly that, an orbiting companion whose stellar wind periodically blocks or modulates the signal over a 16.35-day cycle. Alternatively, some researchers propose neutron star precession, a long-period wobble in the compact object's spin axis that creates a 16-day window during which the emission beam sweeps past Earth. Both models are physically motivated. Neither is confirmed. No companion star has been detected despite sensitive searches at multiple wavelengths. Neutron star precession periods of 16 days don't emerge naturally from standard equations governing neutron star spin-down. They require fine-tuned initial conditions not observed in any confirmed pulsar system, and neither model cleanly explains the specific ratio of active to silent time. In a simple orbital blocking model, the ratio of 4 days on to 12 days off should shift as the companion's atmosphere and orbital geometry evolve across months and years. It doesn't shift. The ratio holds. Multiple fast radio bursts have now been shown to repeat. A second source has its own periodicity near 157 days. The pattern of periodic fast radio bursts, each with a distinct and stable cycle, is becoming a class of phenomenon rather than a single oddity. None of the proposed natural mechanisms fully satisfy the complete set of observational constraints across all examples. What natural process schedules a radio source 500 million light-years away to broadcast for 4 days every 16.35 days with sub-percent precision across years of observation? Why hasn't a companion star been detected if the orbital model is correct? And if something is broadcasting outward on a precise schedule, what is it broadcasting toward? Number 5. The Fermi bubbles. You are astronomer Meng Su at Harvard. It's 2010. You're working through new data from NASA's Fermi Gamma Ray Space Telescope, designed to map high-energy gamma ray emissions across the sky. The galactic center is expected to be a complicated mess of overlapping sources, pulsars, supernova remnants, stellar winds, the chaotic environment around Scrade A star, the 4 million solar mass black hole at the Milky Way's core. You're separating these sources, and when you do, you find something that wasn't in any of the models. Rising from the galactic center, above and below the galactic plane, perfectly symmetric and perfectly matched in size and shape, are two enormous structures glowing in gamma rays. Each one extends 25,000 light-years from the galactic plane. Together they span 50,000 light-years, roughly half the diameter of the Milky Way itself. Nobody had seen them because nobody had known to look. Su published the discovery with colleagues Tracy Sladier and Douglas Finkbeiner in the Astrophysical Journal in November 2010. The structures were confirmed within years by independent instruments at multiple wavelengths. In 2020, the German-Russian eROSITA X-ray satellite released its all-sky survey and found even larger counterparts in X-rays and microwaves matched structures extending 45,000 light-years from the first galactic center, now called the eROSITA bubbles. The original Fermi bubbles sit nested inside them, two concentric pairs of symmetric structures, each pair separately generated, each perfectly matched above and below the galactic plane. Here's what makes this impossible. Natural explosive events in the galactic environment, supernovae, stellar winds, even active galactic nucleus outbursts, produce irregular, asymmetric structures. The turbulence of the interstellar medium scatters and disperses energy in all directions. You don't get matched pairs. You get blobs, arcs, shells with holes torn in them by random turbulence. The Fermi bubbles are bilaterally symmetric to a degree that has no clear natural analog. Both lobes are the same size, the same shape, the same gamma-ray brightness profile. They have sharp, well-defined outer edges, not a gradual fade into the background, but an actual surface where the emission cuts off cleanly. Natural diffusion does not produce sharp boundaries. It produces gradients. The mainstream explanation offers two main candidates. The first is a past episode of intense star formation in the galactic center, a starburst event in which thousands of supernovae occurring close together over a few million years collectively drove a wind of energy above below the plane. The second is a past active galactic nucleus phase of Scras star itself, a period when the black hole was consuming infalling gas at a much higher rate and launching jets of energy outward. Both events are hypothetical. Scrata star is not currently active. No starburst is ongoing. The energy required to produce structures this large and this precisely shaped exceeds what standard models of either mechanism deliver comfortably. The starburst model needs a historical star formation rate in the galactic center far higher than any fossil evidence in the current stellar population supports. The AGN model requires a Scraggia star millions of times more luminous than it is today, sustained over millions of years. Both invoke extreme events that left no direct evidence except the bubbles themselves. And neither explains the bilateral symmetry quantitatively. Why would a starburst, which is an isotropic process, produce two identical lobes pointing perpendicularly away from the galactic plane in matched precision? The discovery of the Erosita bubbles in 2020 made the geometry problem harder. Two separate sets of symmetric structures, each produced by different events, each independently mirrored above and below the plane. The precision accumulates across events separated in time. What energy source produced two perfectly symmetric structures spanning half the Milky Way's diameter? Why are the edges sharp when natural diffusion should produce gradients? What happened at the center of our galaxy 2 to 4 million years ago, and what else did it produce that we haven't found yet? Number 6. The object that shouldn't exist. You are astrophysicist Natasha Hurley-Walker at Curtin University in Perth, Australia. It's 2021. You're reanalyzing archival data from the Murchison Wide Field Array, a radio telescope spread across hundreds of individual antennas in the remote Western Australian outback, designed to survey the southern sky at low radio frequencies. You're hunting transient sources, objects that switch on and off over time. Most transients follow known physics, then one doesn't. An object in the southern Milky Way, approximately 4,000 light-years from Earth, is pulsing radio emission in a way that isn't in any textbook. Every 18.18 minutes, it lights up. The pulse lasts 30 to 60 seconds. Then it goes dark for more than 17 minutes. Then it lights up again. You check the archival data going back months. It has been doing this continuously for the entire span of the records. Hurley-Walker and her team published the discovery in Nature in January 2022. The object was designated Gleam XJ162759, a source in the southern Milky Way that had never appeared in any catalog. What makes the 18-minute period so specifically impossible has to do with the physics of how compact stellar remnants produce detectable radio emission. When a massive star collapses at the end of its life, it can leave behind a neutron star, an object of extraordinary density, spinning extremely rapidly. As it spins, it sweeps a beam of radio emission through space like a lighthouse. That beam is the pulse we detect. Over time, the neutron star loses rotational energy and slows down. Eventually, it crosses what astrophysicists call the pulsar death line, the threshold below which the spin rate is too slow and the magnetic field too weak to sustain the emission mechanism. At that point, the pulsar goes silent. Forever. Here's what makes this impossible. At a rotation period of 18 minutes, any neutron star should have crossed the death line billions of years ago. The standard spin-down equations, validated across hundreds of cataloged pulsars, predict no detectable radio emission from a compact remnant spinning this slowly. Gleam XJ162759 is emitting radio pulses anyway. Each pulse is so energetic it is approximately 1,000,000 times more luminous than the equations predict for an object rotating at this period. It exists far past the boundary where emission is supposed to be physically possible. Its existence means either the equations fail for some class of objects, or this is something the equations don't describe. The mainstream explanations reach for several candidates. One is an ultra-long period magnetar, a neutron star with an extraordinarily strong magnetic field that might sustain emission past the normal death line through an alternative mechanism, but no confirmed magnetar has shown stable, repeating radio emission on this timescale over months. Another candidate is a white dwarf in a binary system, with rotation or orbital period generating the 18-minute signal. but the energy output exceeds known white dwarf radio emission mechanisms by orders of magnitude. What makes the object stranger still is its behavior in time. Active for approximately 3 months in the archival data, then gone. No further detections in subsequent observations. It appeared, pulsed every 18.18 minutes for 3 months, and went silent. No known isolated compact remnant behaves this way. Pulsars don't switch off and on over 3-month windows. Magnetar outbursts have different emission signatures. The 3-month activity window followed by silence fits no clean model. Hurley Walker's team concluded that Gleam XJ162759 likely represents a new class of compact stellar object not yet theorized, or an extreme operating point of known physics at conditions beyond what existing models cover. Since the discovery, at least one additional ultra-long period radio transient has been found in archival data, suggesting these objects exist as a class waiting in old telescope records to be identified. What object pulses every 18 minutes with energy the equations say is impossible? Why did it appear for 3 months and disappear? And how many more are sitting in archival data from the past 2 decades, pulsing in frequencies no one was looking for? Number 7. The cold spot. You are Laura Mersini Houghton, a cosmologist at the University of North Carolina at Chapel Hill. It's 2006. The Wilkinson Microwave Anisotropy Probe has spent years mapping the cosmic microwave background, the oldest light in the universe. The afterglow of the Big Bang emitted 380,000 years after the universe began. In the direction of the Eridanus constellation, there is a region in that ancient light that is colder than everything around it by 70 microkelvins. That number sounds trivially small. It is not. At cosmic scales, a temperature depression of this size and extent is a statistical event that standard cosmology says should essentially never happen. You've been running the numbers, and your conclusion is that the cold spot was not created by anything inside this universe. Something outside pushed against ours before the Big Bang. The cold spot was first identified in 2004 from WMAP data and subsequently confirmed at higher precision by the European Space Agency's Planck satellite. It spans roughly 1.8 billion light-years on the sky, making it one of the largest coherent anomalies ever detected in the cosmic microwave background. That background is the baseline record of the universe as it existed 13.8 billion years ago. Whatever left its mark, there did so before the first galaxies, before the first stars, before anything we would recognize as structure had formed. The cold spot's imprint is that old. It corresponds to a real physical structure in the modern universe, a supervoid, a region of space containing significantly fewer galaxies than average. Astronomers at Durham University confirmed the supervoid in a 2017 galaxy survey. A supervoid can cause CMB photons to lose a small amount of energy through the integrated Sachs-Wolf effect, a temperature imprint left as photons climb out of a shallower gravitational well than expected. This is a genuine physical mechanism. The problem is that the supervoid doesn't account for the full magnitude of the temperature deficit. It explains part of the anomaly, not all of it. The mainstream explanation holds that the cold spot is a statistical fluctuation, one of the unavoidable random temperature variations that any random field produces. The universe is large enough that even a 1 in 1,000 event has to appear somewhere. The cold spot, in this view, is just where the lowest dice roll landed. Combine that with the partial supervoid contribution, and you have a plausible natural account. Here's the problem. The supervoid itself is the issue. A void 1.8 billion light-years across requires an initial underdensity in the early universe that is also anomalously large. You're not just explaining one anomaly, you're stacking 2 statistically rare events on top of each other to explain a third. The explanatory chain grows fragile. When researchers calculate the probability of the cold spot arising from standard inflationary cosmology, accounting for both the temperature deficit and the associated supervoid, the combined probability consistently falls between 0.1 and 1%, depending on the analysis. Mersini Houghton and her colleagues proposed a different origin. During the quantum fluctuation epoch, immediately preceding or coinciding with inflation, our universe was in quantum entanglement with neighboring bubble universes. A bubble universe adjacent to ours exerted a gravitational influence on the matter distribution in our region before inflation froze the structure in place. The resulting underdensity was then carried through 13.8 billion years of cosmic evolution and shows up today as both the cold spot in the CMB and the supervoid in the galaxy distribution. The model makes predictions that match the observed characteristics, the location, the temperature profile, the associated void size, and it implies that direct physical evidence of another universe is sitting in the oldest light we can observe. Is the cold spot a statistical fluke, a scar from a pre-Big Bang collision with a parallel universe, or something our physics hasn't named yet? And if another universe can leave a physical imprint we can measure in the oldest light in existence, how long have we been looking at that mark without recognizing what it is? Number 8. Tabby's star. You are Tabetha Boyajian, an astronomer at Yale, in 2015. Your Planet Hunters project, a citizen science effort in which volunteers comb through Kepler Space Telescope data for anomalous light curves, has flagged a star in the constellation Cygnus 1,470 light-years away, labeled KIC 8462852. You pull up the light curve. A star's brightness should stay roughly constant when measured over days and weeks, varying by a fraction of a percent due to ordinary stellar activity. KIC 8462852 dims by 22%. Not a fraction of a percent, 22%. In an irregular pattern, with no repeating cycle that fits a planet, a debris ring, a comet, or anything in the standard catalog. You've been working in astronomy long enough to know this doesn't happen. KIC 8462852 became known as Tabby's star or Boyajian's star, after the paper Boyajian and her collaborators published in Monthly Notices of the Royal Astronomical Society in 2016. The light curve anomalies from the Kepler dataset were striking on their own. Multiple distinct dimming events of varying depth and duration, some lasting a day, some a week. With an asymmetric profile, the brightness doesn't drop and recover symmetrically. Jupiter, the largest planet in our solar system, would cause roughly 1% dimming as it transits a star of this size. Tabby's star was dimming by 22%. Whatever was blocking that light was enormous. Then, astronomer Bradley Schaefer published an analysis in 2016 showing that Tabby's star had dimmed by approximately 20% between 1890 and 1989, visible in historical photographic plate archives going back more than a century. Not the fast dips. The baseline brightness of the star itself had been steadily declining over 130 years of continuous observation. The same star dimming dramatically in fast, irregular events, and also steadily fading across 130 years, is a problem no simple natural model cleanly addresses. Here's what makes it impossible. The most widely accepted natural explanation for the short-duration dips is a swarm of cometary fragments or dusty material orbiting the star and periodically crossing our line of sight. Dust clouds work for some features of the dimming profile. But here's the specific problem. If enough dust exists to block 22% of the light from a star, that dust absorbs stellar energy and re-radiates it as infrared heat. Astronomers searched for that infrared excess with the Spitzer Space Telescope. It was not there at the level required for the amount of dust the dimming depth demands. The dust hypothesis requires an enormous quantity of material to explain the dimming, and then that material has to be nearly invisible to infrared detectors. Both conditions simultaneously, massive light blocking and minimal infrared signature, are very difficult to satisfy. Penn State astronomer Jason Wright noted in a 2015 paper in the Astrophysical Journal that the anomalous light curves of KIC 8462852 were what astronomers would expect to see if a civilization were constructing a Dyson sphere or similar megastructure. Around a star, a partially assembled structure, irregular and asymmetric, blocking variable amounts of starlight depending on which segments occupied the line of sight. He was not claiming this was the explanation. He was documenting that the data fit it, and that it was worth ruling out before settling on natural alternatives. The century-long dimming trend is the harder problem. Cometary swarms explain episodic fast dips. They don't steadily reduce a star's baseline brightness for more than 100 years. Each natural candidate, dusty clouds migrating into the line of sight, intrinsic stellar variation, asymmetric debris disks, fails on at least one specific observable when tested against the complete dataset. No single model, natural or otherwise, explains the fast, irregular dips, the asymmetric light curve profiles, the insufficient infrared emission, and the 130-year secular dimming trend simultaneously. What process causes a star to dim by 22% in irregular bursts and steadily over 130 years at the same time? Why is there no infrared excess at the level the dust hypothesis requires? And if every proposed natural explanation has a specific failure point, what does that leave? Number 9. The axis of evil. You are Kate Land, a cosmologist at Oxford University, in 2005. You've been analyzing the quadrupole and octupole moments of the Wilkinson microwave anisotropy probe data, the two largest scale temperature pattern components in the cosmic microwave background, encoding information about the geometry of the entire observable universe. These patterns should be random. Cosmological theory is built on the assumption that the universe has no preferred direction, no special axis, no orientation. The technical term is isotropy. The universe looks the same from any vantage point in any direction. What you're finding is that it doesn't. The quadrupole and octupole are aligned with each other. They align with the ecliptic plane of our solar system, and they align with the direction of the CMB dipole, the axis describing our own motion through the universe. 3 independent alignments, all converging on the same axis. An axis that points directly at us. The paper Land wrote with physicist João Magejo appeared in Physical Review Letters in 2005. They named the alignment the axis of evil. The name wasn't theatrical. In cosmology, evil describes an anomaly so persistent and structurally resistant to standard explanation that it threatens the theoretical framework surrounding it. Isotropy, the large-scale randomness of the universe, is one of the foundational pillars of modern cosmological theory. If the largest scale structures in the cosmic microwave background are aligned with the geometry of our own solar system, that foundation is broken, and broken precisely along an axis that runs through our backyard. Here's where it gets strange. The probability of the quadrupole and octupole aligning with each other by chance is already low, a few percent at best. The probability of that aligned pair also aligning with the ecliptic plane of our solar system is lower still. The probability of all 3 quadrupole, octupole, and CMB dipole converging on the same axis is somewhere between 0.1 and 1%, depending on the analysis method. Multiple independent research groups using different statistical techniques have reproduced the finding with similar probability assessments. In 2013, the European Space Agency released data from the Planck satellite, a more sensitive instrument than WMAP, with better calibration and substantially improved foreground removal. The Planck team's analysis of large-scale CMB anomalies confirmed the alignments found by Land and Magejo. With better data, more careful treatment of foreground emission from the Milky Way's own dust and gas, and independent methodology, the axis was still there. The Planck collaboration's own published papers describe the alignment as anomalous and note that it is not explained by known systematic effects in the instrument. The mainstream explanation points to foreground contamination emission from dust, gas, and free electrons in our galaxy that bleeds into the CMB maps and could create apparent alignments at large angular scales. This is a legitimate concern and was the leading alternative explanation for years. The Milky Way is bright at microwave frequencies, and separating its emission from the primordial CMB requires sophisticated modeling, but Planck was specifically designed to address this. Its higher sensitivity and 7 frequency channels allowed far more sophisticated foreground separation than WMAP. After Planck's improved foreground removal, the alignments remained. The foreground contamination argument was tested with the best tools available, and the anomaly survived. No physical mechanism in standard cosmology connects the orbital plane of our solar system to the large-scale temperature structure of the universe. The ecliptic plane is a local feature, the plane in which Earth orbits the Sun. The CMB encodes the geometry of a universe 93 billion light-years across. In known physics, there is no pathway by which one influences the other. The universe's oldest light carries an axis. That axis points toward our solar system. If the Copernican principle is false, if we occupy a position that is in some physical way special, what does it imply about every cosmological calculation we've made while assuming we don't? Number 10. The Great Attractor. You are Alan Dressler, an astronomer at the Carnegie Institution in Washington. It's 1987. You're part of a collaboration of 7 astronomers later nicknamed the Seven Samurai, who have spent years measuring the velocities of 400 elliptical galaxies spread across a large volume of the nearby universe. The goal was to test the uniformity of cosmic expansion. What you've found instead is that the measured velocities don't match. Galaxies that should be receding from each other at rates set by the Hubble expansion are instead moving in addition to that expansion at 600 kilometers per second toward a single region of sky. All of them. The Milky Way, the local group, thousands of galaxies across several 100 million light-years of space, all streaming toward the same point. Not because of the expansion of the universe, because something is pulling. The team published in the Astrophysical Journal in 1987 and named the source of the pull the Great Attractor. It is located approximately 150 to 250 million light-years from Earth, in the direction of the constellations Centaurus and Hydra. Initial estimates put the mass required to produce the observed infall at roughly the equivalent of tens of thousands of individual galaxies. Subsequent surveys identified the Norma cluster, a large concentration of galaxies in the Great Attractor region, as a major contributor. Later work pointed to the even more distant Shapley supercluster, 700 million light-years away, as an additional component. Both are real, both are massive, and both contribute to the flow. Here's what makes this impossible to fully resolve. Even after accounting for the Norma cluster and the Shapley supercluster's combined gravitational influence, residual bulk flow anomalies remain in the galaxy velocity data. The accounting doesn't close. There is still unexplained infall toward the Great Attractor region that isn't attributed to any identified mass concentration. The dark matter distribution required to fully explain the observed motions is inferred from the velocities themselves. We don't observe it directly. We calculate what must be there to produce what we see. The Great Attractor sits in the zone of avoidance, the region of sky obscured by the dense dust and gas of the Milky Way's own disk. Our galaxy blocks optical, infrared, and even some radio wavelengths in that direction. For decades, we couldn't see what was at the center of the pull because our own galaxy was in the way. Subsequent X-ray and radio surveys have partially pierced the zone of avoidance, confirming the Norma cluster. But a substantial fraction of the direction remains obscured, and whether all the required mass has been found is still unresolved. In 2014, Brent Tully and his colleagues published a paper in Nature mapping our supercluster named Laniakea, meaning immeasurable heaven in Hawaiian. It spans 500 million light-years and contains roughly 100,000 galaxies, including our own. The Milky Way sits on the outer edge of Laniakea, near the gravitational boundary between 3 intersecting basins. The center of Laniakea's gravitational basin lies near the Great Attractor region. We live on the rim of a vast cosmic structure, and that structure is itself flowing towards something only partially identified, partially visible, and still partially unexplained. The mainstream explanation holds that the Great Attractor is a large mass concentration of galaxy clusters and dark matter whose combined gravity drives the observed flows, and that improved surveys will eventually account for all the residual motions as they identify more mass in the zone of avoidance. This may be correct. The residual anomalies have shrunk as surveys have improved, but we are embedded inside the flow. We cannot step outside our own motion to measure it cleanly. We are falling toward the Great Attractor at 600 kilometers per second, and the accelerating expansion of the universe means we will never arrive. The most distant parts of the attractor region are being carried away from us faster than we can close the gap. We are in a permanent fall toward an unreachable destination, pulled by something our own galaxy partially hides, that our equations only partially account for, that has been drawing at us since before our sun existed. 10 anomalies. A flow pulling everything toward something beyond the edge of existence. 234 sun-like stars sharing a signal no stellar physics explains. A visitor from interstellar space that accelerated without propulsion and waited in our path. A radio source 500 million light-years away broadcasting on a precise schedule. 2 gamma-ray structures too symmetric for any natural process we know. An object pulsing at frequencies that should have gone silent billions of years ago. A scar in the oldest light from a collision with a parallel universe. A star dimming in patterns nothing fully explains. An axis in the universe's oldest light that points at our solar system. and a gravitational pull towards something our own galaxy partially hides. The signals have been in the data for decades. What they mean is the question no one has answered. Subscribe if this is the kind of thing you want to keep thinking about. Leave a like, and let us know in the comments where you're watching from.